In mathematical logic, a theory is a set of sentences in a formal language. Usually a deductive system is understood from context. An element of a theory is then called an axiom of the theory, and any sentence that follows from the axioms in a deductive system that satisfies the principle of explosion. This is equivalent to requiring that there is no sentence phi such that both phi and its negation can be proven from the theory. A satisfiable theory is a theory that has a model. This means there is a structure or M that satisfies every sentence in the theory. Any satisfiable theory is syntactically consistent, because the structure satisfying the theory will satisfy exactly one of phi and the negation of phi for each sentence phi. A consistent theory is sometimes defined to be a syntactically consistent theory, and sometimes defined to be a satisfiable theory. For first-order logic, the most important case, it follows from the completeness theorem that the two meanings coincide. In other logics, such as second-order logic, there are syntactically consistent theories that are not satisfiable, such as omega inconsistent theories. A complete consistent theory is a consistent theory T such that for every sentence phi in its language, either phi is provable from T or T phi is inconsistent. For theories closed under logical consequence, this means that for every sentence phi, either phi or its negation is contained in the theory. An incomplete theory is a consistent theory that is not complete. See also omega consistent theory for a stronger notion of consistency. Interpretation of a theory. An interpretation of a theory is the relationship between a theory and some contensive subject matter when there is a many-to-one correspondence between certain elementary statements of the theory and certain contensive statements related to the subject matter. If every elementary statement in the theory has a contensive correspondent, it is called a full interpretation. Otherwise it is called a partial interpretation. Theories associated with a structure, or each structure has several associated theories. The complete theory of a structure A is the set of all first-order sentences over the signature of A which are satisfied by A. It is denoted by TH. More generally, the theory of K, a class of sigma structures, is the set of all first-order sigma sentences that are satisfied by all structures in K, and is denoted by TH. Clearly TH equals TH. These notions can also be defined with respect to other logics. For each sigma structure A, there are several associated theories in a larger signature sigma that extends sigma by adding one new constant symbol for each element of the domain of A. The cardinality of sigma is thus the larger of the cardinality of sigma and the cardinality of A. The diagram of A consists of all atomic or negated atomic sigma sentences that are satisfied by A and is denoted by diagar. The positive diagram of A is the set of all atomic sigma sentences which A satisfies. It is denoted by diag plus A. The elementary diagram of A is the set L diagar of all first-order sigma sentences that are satisfied by A, or, equivalently, the complete theory of the natural expansion of A to the signature sigma. First-order theories. A first-order theory is a set of sentences in a first-order formal language. Derivation. In a first-order theory there are many formal derivation systems for first-order logic. Syntactic consequence. In a first-order theory, a formula A is a syntactic consequence of a first-order theory if there is a derivation of A using only formulas in as non-logical axioms. Such a formula A is also called a theorem of. The notation indicates A as a theorem of interpretation of a first-order theory. An interpretation of a first-order theory provides a semantics for the formulas of the theory. An interpretation is said to satisfy a formula if the formula is true according to the interpretation. A model of a first-order theory is an interpretation in which every formula of is satisfied. First-order theories with identity. A first-order theory is a first-order theory with identity if includes the identity relation symbol equals and the reflexivity and substitution axiom schemes for this symbol. Topics related to first-order theories: compactness theorem, consistent set, deduction theorem, enumeration theorem, Lindenbaum's lemma, Lowenheim-Skolem theorem. Examples: one way to specify a theory is to define a set of axioms in a particular language. The theory can be taken to include just those axioms, or their logical or provable consequences, as desired. Theories obtained this way include ZFC and Pinot arithmetic. A second way to specify a theory is to begin with a structure and then let the theory be the set of sentences that is satisfied by the structure. This is one method for producing complete theories, described below. Examples of theories of this sort include the sets of true sentences in the structures N, where N is the set of natural numbers and R is the set of real numbers. The first of these, called the theory of true arithmetic, cannot be written as the set of logical consequences of any enumerable set of axioms. The theory of was shown by Tashi to be decidable. It is the theory of real closed fields.